sharing screen and good stuff like that. Okay, the quiz is now too late to submit, so that means I can go over it. Okay, so number 1, x plus 10 or 1x plus 10 over x minus 4x plus 3, a over x minus 4 plus b over x plus 3. Okay. And this is considered, you might recall, type 1, so most likely on the test on Thursday I'll give you something like that. If I have one of the other types, it'll only be a setup where you just set up this part here, let's say, and then you can stop. Okay, get a common denominator, multiply this side by x plus 3 over x plus 3, this side by x minus 4 over x minus 4. Get ax plus 3a plus bx minus 4b over x minus 4x plus 3. Put these together as a plus bx plus 3a minus 4b. This has to equal 1. This has to equal 10. So a plus b equals 1. 3a minus 4b is equal to 10. Multiply the top equation by 4. That gives me 4a plus 4b equals 4. Add them up. B's drop out. 7a equals 14. So a is equal to 2. If a is equal to 2, that means b is equal to negative 1. So my original integral is now 2 over x minus 4 minus 1 over x plus 3. So 2 ln absolute value of x minus 4 minus ln absolute value of x plus 3 plus c. Okay, question 2. From that chart, this was the middle one that had the plus. So let x equal 5 tangent theta. Dx equals 5 secant squared theta d theta. Okay. And just so you know where it is again, from 7.4, that tells you which one to choose. Sorry, 7.3. That was this thing, right? So it's on page 486. So all of this stuff, right? All right, so x is 5 tan theta, dx is 5 secant squared theta d theta. So the numerator is 5 secant squared theta d theta, that's dx, over radical x squared plus 25. So square that, 25 tangent squared theta plus 25. Factor out to 25, you have tangent squared theta plus 1. That's equal to secant squared. So I have on the denominator square root of 25 secant squared theta, which comes out to be 5 secant theta. 5 cancels out, secant theta cancels out. Integral of secant theta, we went over that. And by the way, if you want to put that on your cheat sheet on the test, you may. So that's ln absolute value of secant theta plus tangent theta plus c. Okay, now change back to x. So we said x was equal to 5 tangent theta. Divide both sides by 5. Theta is x over 5. So here's theta, here's a right angle. So tangent is opposite over adjacent. So opposite is x, adjacent is 5. You can do your a squared plus b squared equals c squared, or the trade secret, so to speak. Just look back at the original problem, and you're probably correct. Square root of x squared plus 25. But let's double check. What is this thing squared? X squared. What is this thing squared? 25. Add it up. X squared plus 25, which is the square of this. All right, so we have ln absolute secant. Secant is the reciprocal of the cosine. So that's hypotenuse over adjacent. Cosine is adjacent over hypotenuse. So secant is hypotenuse over adjacent. Plus tangent is x over 5, opposite over adjacent. Okay, now I will accept this. So if you leave something like this on a test, that's fine. But the absolute best you can do with that, you could get a common denominator of 5. I can write this as ln absolute radical x squared plus 25 plus x minus ln 5. The log of a quotient is the difference of the logs. Okay, And then you can realize that C can be any real number. So if C is any real number, C minus ln 5 also runs through all the real numbers. So you can just swallow up negative ln 5 plus C as just C. Okay, and I think I went over something like this before, but this expression is always positive. This can never be negative, it can never be 0. So you can actually drop the bars here. And let me see if I can run through quick derivation of that again. Okay, if x is 0, this is clearly positive, right? Put a 0 there, square root of 25. If x is positive, it's certainly going to work. Okay, now what if x is negative? Okay, the logic I'll give you is, pretend that 25 isn't there. Suppose I plug in negative 2. Negative 2. What's negative 2 squared? 4. Square root of 4, 2. 2 plus a negative 2, 0. Okay. But if I add anything to it, that's going to make this bigger than this in absolute value. So this is bigger than this. That logic works for any number. Okay. Suppose I say plug in negative 10, any negative. Ignore the 25. Put negative 10 there, negative 10 there. Negative 10 squared, 100. Square root, 10. 10 plus a negative 10 is 0. Okay, so they match, which means if I put a plus 25, this is going to be bigger. All right, so the absolute best answer is this. But on the exam, if you left it like this or like this, that's fine. All right, and speaking of the exam. Okay, so again, I'm a little bit ahead. I was only supposed to do 7.8 today. I was done with 7.8. I'm completely done with it, so I'll do 8.1. Okay. I was going to turn today into a big question and answer session, so I'll lecture for a while, let you ask stuff. Okay, and then Thursday, I'll either do 8.1 or sneak in some of 8.2. I'll still be ahead no matter what. Okay. I wasn't going to lecture that long on Thursday. Let you ask questions, break, and then take the test. Okay. So maybe on Thursday, I was going to lecture maybe 30, 40 minutes at the most. That would take us to, what, 7:30, 7:40? Okay. Then let you ask questions. And then if we stop early, I can start the test early. That's perfectly fine by me. Okay, now a review of the ground rules for the test, because last time it wasn't really the rules that I wanted to, because last time when you took the test, my internet was down, right? So this is our first test in the ideal condition, so to speak, for me. I mean, providing my internet doesn't go down between now and Thursday, or I don't get sick or whatever. Okay, so ground rules. This is what you turn in for homework. You can turn it in early. I'll take it anytime Thursday is fine if you want to turn it in early. Okay, so again, ground rules for Thursday. I will lecture, maybe 8.1, 8.2. I don't have to go that far. I'll stop, let you ask questions. We break, and then after the break, we'll take the test. Now, during the break, I will either email you or put on Canvas announcements the test, but I'll also project it. Okay, I'll project it here because that might be better for some of you. Canvas announcements, one nice thing is if you have a printer, you can print it, then you've got it in front of you. Okay, so the latest I'll stop the first half on Thursday will be 8:20, we said. I'm hoping it doesn't go that long. In my syllabus, I only promise you 50 minutes. All right, so 8:20, 10-minute break, 8:30. Takes 5 minutes to give you everything and make my announcement, and that gives you from 8:35 to 9:25. All right, so, but if we start early, that's fine. So if we start the test at, let's say, 8:20, 8:15, that's okay by me. And then we'll stop at 9:25. Okay, so ground rules again for this test. This is a first test of this nature. So you have to have your video on. You must have your video on. I need to see you. I will take row second half also while you're taking the test. So if you're trying to do the trick of not showing up but then turning in the test, I will know. I won't call your name during the test. I don't need to, I got plenty of time to take row just by looking at the participant list, right? Okay, so if I find out your name's not there, but I get a test from you, I'm just going to say, no, that doesn't count. You're going to get a 0. Okay. What else? During the test, you will mute yourselves. So, nobody wants to hear the background noise. But show your camera. I need to see your camera. Enough of yourself so that I can see what you're doing. Have your actual background. So no Golden Gate Bridge, no, all green or outer space or anything like that. I need your actual background so I can see what's going on behind you, as the case may be. Okay, I'll close class as usual at 9:25. Then, so I'll turn off the meeting. You have 5 minutes to turn in your test. So just get out your cell phone and click, 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 click. Or if you have a scanning program like Cam Scanner, you can use Cam Scanner. You have 5 minutes to submit it. So I need to test by 9:30, even though I would have closed the meeting. And you have until 10 o'clock, another half an hour to turn in the homework, which means you turn in all of this. I have a 70% requirement. So if you don't turn in at least 70% of the homework, I won't count your test. It has to be in by 10 o'clock. But again, if you want to turn in the test early, Thursday morning is fine, or Thursday afternoon, that's fine also. Okay. In actuality, how much do I end up doing, right? I end up doing almost half, maybe even more than half, a little bit less than half. 70% shouldn't be that hard of a requirement to turn in for the test itself. Okay, so this is the first time we're taking a test in the actual scenario that I wanted. And let's see, what else? So again, during the break, I'll try to put on Canvas announcements to test so you can look at it there. But I'll project it also because maybe that's better for some of you. But if I project it, you'll have to get your cell phone out and take pictures because I need to take it down after a minute so I can see everybody. So have your video on. I need to see that you're not cheating and stuff like that. You can have your calculator. You can have your cheat sheet. Okay, so again, front and back, put whatever you want, both sides. You don't have to turn that in. I don't need your cheat sheet. But of course, you can't use anything else. No books, no notes, no computers, no other people, nothing like that for the exam. Okay, so that's that. Does anybody want to ask a quick question about the test or the format since this is our first time like that? Anybody want to say anything? Or you can say it later also. Okay, some of you might have it in chat. I can't see the chat now into this mode. So I'll address the chat later. I mean, I can do it at the second hand, so that should be fine. But let me go ahead and get started with 8.1. Okay, I'm changing the assignment a little. It's 1, 2, and 7 to 19 odd. Okay, the numbering that I had before was for the 7th edition. I realize this is the 8th edition now, and I have to change some of the numbers here. So 1, 2, 7 to 19 odd. So go ahead and take notes or just watch the video later. 8.1 is not on the test this Thursday. 8.2 is not on the test this Thursday if I get to that. So not to worry about that. All right, so let me get started. Yes, I know the chat is blowing up. There's about 17 or 18 there, but we'll see. So I'll get to it later, but let me get started with 8.1. Okay, so 1, 2, 7, and 19 odd. All right, so what is going on in 8.1? We're doing arc length. Arc length. So here's a function. We can talk about area under the curve. We know what that's about. We can talk about revolving this thing about the x-axis or y-axis. We know what that's about. Well, now let's consider the arc length. If I were to walk along this curve, how far would I have walked, right? Walking along here. All right, so if we were meeting face-to-face, I would spend more time on the derivation. I won't. I'll just talk about it very quickly. But the usual calculus technique, if I chop this up into so many pieces, right? Chop it up in a whole bunch of pieces, and I break it into this segment, and this segment, and this segment, and I add them all up, that would be only an approximation, right? If I added them up. But as usual, if I chop this up, if I chop into a million pieces and do the same thing, the approximation gets better and better and better, right? The usual trick that if n approaches infinity, which means delta x approaches 0, then the approximation gets better and better and better. Now, if you look at what I have here, okay, the distance from here to here, we could call that delta x. The distance from here to here is like a delta y. This would be like a hypotenuse. Okay. So I'll just add up the length of this hypotenuse plus this hypotenuse plus this hypotenuse and so on. Okay. Let delta x approach 0, let n approach infinity, and then we would have an expression for the arc length. Okay. So I mean, if you imagine taking this, chop it up in a million pieces, chop, real fine, then the arc length is going to be real close to adding up all the lengths of the hypotenuses. Right? All right, so they even have that over here somewhere. You don't have to write any of this down. A tiny little line segment is the square root of delta x squared plus delta y squared, right? Like this. delta x, delta y. Or look at these pictures as you look at the progression from here to here to here to here, right? This approximation gets better and better and better as I let n get bigger and bigger. All right, to do some more fancy footwork with the algebra, and I'll just tell you what the result comes out to be for the arc length. Okay, so on page 545, arc length formula. I think this is the easiest one to use. This is equivalent, but I like this one better. So the arc length is the integral from a to b of the square root of 1 plus dy dx squared dx. Okay, and you can put that on your next formula sheet. You know, my advice is don't even put it until after the test on Thursday, but you know, put this. So here's the formula for arc length. If I travel along an arc, right? I travel along here, and here's the function. What's the arc length? If I were to walk along that curve, how far do I walk? Use this formula. Okay? So integral from a to b of the square root of 1 plus dy dx squared dx. Okay? And I'll hasten to add, this is only if you have y as a function of x. Suppose you have x as a function of y, it's probably not that hard to figure out how that would change. Instead of dy dx, can you guess what it would be? It'd be dx dy. And then this would be a dy also. Okay, so there's two variations of the formula. Arc length is integral from a to b of square root of 1 plus dy dx squared dx. You can put that on your cheat sheet. Or the other variation is if you have x as a function of y, page 546, integral from c to d of radical, just as we talked about, 1 plus dx dy squared dy, where x is a function of y. Now that even sounds weird because we've always been doing y is a function of x, y is a function of x, y equals f of x. It doesn't have to be. You can have x as a function of y, then it would just look like this by analogy, 1 plus dx dy squared dy. Okay, so that's all. All right, so I'll get started with doing a bunch of problems with that. Okay, so 1, 2, 7 through 19. Let me try to run through a lot of these. Okay, I may decide not to do 1 or 2, but we shall see. Okay, problem number 9. You don't have to graph these in general, not necessarily graph. Okay, 1 plus 6x to the 3 halves from 0 to 1. Okay, so this has some curve, right? It looks like something. We don't really care about what it looks like. It looks like something. So I'm walking along that curve from 0 to 1. Well, we can do that. If I plug in 0, I'm at 1. So 0, comma 1, right? When you plug in 1, you get 7. Okay, so I'm going from 0, comma 1 to 1, comma 7 along this curve. Okay, let's just say look something like that. We don't really care. How long is the length of the curve? All right, so I throw it in the formula. Here's the formula. Integral from a to b of 1 plus dy dx squared dx, or 1 plus dx dy squared dy if you have x as a function of y. Okay, so I need the derivative. That's easy. Derivative of 1 is 0. Derivative of this is 3 halves times 6 is 9 x to the 1 half, which is 9 radical x. Okay, by formula, I'm supposed to square it. So the square of this is 81x, and then I add 1. So 1 plus 81x. So that goes underneath the square root. Okay, so one more time. 1 plus dy dx squared. So find dy dx, the derivative. There it is. Square it. There it is. Add 1. So I'm integrating from 0 to 1. Very nice. You can't get better than integrating from 0 to 1. Of the square root of this thing. Radical 1 plus 81x dx. So here we go. All right, and we know how to do that. That's 1 plus 81x to the 1/2 power. So there's going to be a chain rule going on here. If I were to differentiate, I would multiply by 81, since I'm integrating, I would divide by 81 or multiply by 1 over 81. Okay, so if I just go by the power rule, I have 1 plus 81x to the 3 halves divided by 3 halves. If you divide by 3 halves, you multiply by 2/3, and then there's the 1 over 81 by the chain rule. Okay, so one more time, you add 1, 3 halves, divide by 3 halves means times 2/3, and then by the chain rule, if you differentiate, you would multiply by 81. When you integrate, you multiply by 1 over 81. Okay, and by the way, this section, you're going to have a lot of that because that's already in the formula, right? Here's the formula. So if you're integrating this, unless there's something special going on, it's generally going to be blah, blah, blah to the 1/2. So when you integrate blah, blah, blah to the 1/2, you're going to have a 3 halves, and then divided by 3 halves means times 2/3. So that theme is going to be there quite a bit. Okay, so that times that comes out to be 2 over 243. Plug in 1, you have 82 to the 3 halves. Plug in 0, you have 1 to the 3 halves. Well, 1 raised to anything is 1. Okay, now there's a certain way you're supposed to write this. And this theme will happen a lot in this section because you're going to have a lot of this 3 halves stuff. Okay, when you have 82 to the 3 halves, okay, we're going to write it like this as our standard. 82 radical 82. So here's my final answer. 2 over 243, 82 radical 82 minus 1. Okay, so let's talk about the algebra here. This is like 82 to the first power. This is 82 to the half. So you have 1 plus a half, 3 halves. All right, so this is the way I want you to write it in general. So if you don't do this step, I can take out points. Okay, so how do you write, let's say, 7 to the 3 halves? 7 radical 7. How do you write 40 to the 3 halves? 40 radical 40. How do you write x to the 3 halves? X radical x. You'll see that more often here. Okay. Okay, problem number 11. Y equals x cubed over 3 plus 1 over 4x. And you're going from 1 to 2. Okay, so you see what's happening. This has some shape. You can use techniques from Calc 1 to figure out what it looks like, but whatever it looks like. And you're going from x equals 1 to x equals 2. We're finding out the arc length. How long is it if I walk along the curve? All right, so first I'm going to write this as 1/4 x to the minus 1. That's better for differentiation purposes, right? All right, so dy dx, derivative of this is x squared. Derivative of this is minus 1/4 x to the minus 2. Now I'm supposed to square it. Okay, so we have this interesting theme here for squaring this thing. So x squared minus 1/4 x to the minus 2. So I have to square this. That's like my a, that's like my b. Okay, so my a squared is x squared squared x to the 4th. My b squared, I square this. 1/4 squared is 1/16. X to the minus 2 squared is x to the minus 4. Okay, now here's the tricky thing about the middle. 2ab minus 2ab. So it's 2 times this times this. 2 times a 4th. 2 times a 4th is a half. And now this. What's x squared times x to the minus 2? That's x to the 0, which is 1. So the middle term is just minus a half. How do you like that? So I'm doing a minus b squared, a squared minus 2ab plus b squared. So a squared is x squared squared, there it is. B squared is 1/16 x to the minus 4. And the middle term is minus 2ab. So minus 2 times that times that. 2 times a 4th is 1/2. X squared times x to the negative 2. I'm supposed to add the exponents. That's x to the 0, which is 1. So I have negative a half. Now, I'm supposed to add 1. 1 plus all of this. If I add 1, all that happens is if I take negative a half plus 1, it becomes a positive a half, does it not? Here's the second derivative. Oh, sorry, not the second derivative. dy dx squared. Take it back. The square of the derivative. Plus 1. Well, negative a half plus 1 is positive a half. That turns out to be a perfect square. If you stop and think about what happened over here, when I squared this, I had negative a half. The only difference between this and this is instead of a minus, it's a plus, which means I can factorize this back into the exact same thing as this, except change it to a plus. So in other words, I claim if you factor this, you get this. And if not sure, multiply it back out. Okay, that theme will show up quite a bit in this section and also the next section. Okay, so if you want to check, square this, there it is. Square this, 1/16 x to the minus 4. And then the plus 2ab plus 2 times 1/4 is a half. And then x squared times x to the minus 2, there's a 0. Okay, so that's a clever thought. That theme shows up quite a bit in this section and section 2. Okay, that goes underneath the square root, but you can see what happens, right? If you have the square root of a square, just take out the square root in a square. So I just have x squared plus 1/4 x to the minus 2 dx. Okay, so I think you can take it after a certain point, so I just say etc. But you know, that's x cubed over 3 plus 1/4 x to the minus 1 over minus 1. Clean up the algebra a little bit. 1/3 x cubed minus 1 over 4x from 1 to 2. Okay, the rest is just plugging in, so I said etc. I decided to save class time. You can take it from there. But you know, plug in 2, figure it out, plug in 1, and then combine like terms. So you do that. I've done the hard work right here. Okay. All right, next one I'm going to show you was 13. This is x as a function of y. X equals 1/3 radical y, y minus 3, as y goes from 1 to 9. I think you can see how the difference would be. It would be 1 plus not dy dx squared. It would be dx dy squared, and this would be a dy. Okay. So even this looks funny because we're used to saying y equals a function of x. But hey, x can be a function of y. There's no law against that. So here we go. All right, let's distribute. Radical y times y, that's y to the 1/2. That's y to the 1. So that's y to the 1.5. So 1/3 y to the 3/2. And then if I multiply these two, what's 1/3 times negative 3? Negative 1. And then radical y is y to the 1/2. So this, after you distribute and write it like this, comes out to be this. Okay? Okay, that's y to the 1/2 times y to the 1, y to the 3/2. Then negative 1/3 times 3 is 1, so negative y to the 1/2. Okay, so now I'm going to write dx dy. It even sounds funny to say it, but instead of dy dx, it's just a role reversal for x and y, dx dy. Okay, so that times that is 1/2 y to the 1/2 minus 1/2 y to the negative 1/2. Okay, so here's my dx dy. Then I'm supposed to square it. Okay, so it's a similar kind of game as over here. If you square this, 1/2 squared is 1/4. Y to the 1/2 squared is y. Or think of this as radical y. Radical y squared is y. This one squared is 1/4 y to the negative 1. Right, if you multiply negative 1/2 by 2, you get a negative 1. And there's that similar theme again. I claim the middle one is just negative 1/2. The middle is 2ab minus 2ab. So what's 2 times 1/2? 1 times 1/2 is 1/2. And then I multiply these two. So what's y to the 1/2 times y to the negative 1/2? Same as the previous problem. That's y to the 0. I add the exponents, right? And y to the 0 is 1. So here's the derivative, dx dy squared. I add 1. Well, just like before, if you add 1, all that happens is that minus 1/2 becomes plus 1/2. Everything else is the same. So it's 1/4 y plus 1/2 plus 1/4 y to the minus 1. And again, similar theme to over here. this factors into a perfect square. It's exactly the same as this, except instead of a minus, it's a plus. So this stuff factors into 1/2 y to the 1/2 plus 1/2 y to the negative half squared. Okay, if you can't see it, it's exactly the same as this, except change that to a plus. Okay, 1/2 y to the half plus 1/2 y to the negative half squared. Okay. All of that goes underneath the square root of the formula. And you can see if you have a square root squared, you just squiggle out the square root and the squared. So again, you're just integrating from 1 to 9, 1/2 y to the 1/2 plus 1/2 y to the negative 1/2. And here's another where I'll just say etc. I'll let you figure it out after a while. I'll show you the integration. So 1/2 y to the 3/2 divided by 3/2 means times 2/3. Looks like these cancel out. 1/2. Integrate y to the negative half. So if you add 1, that's y to the 1/2. Divided by 1/2 means multiplied by 2. These cancel out. Okay, then again, I'll just say etc. And you take it from there. All right, so you plug in, 9 and 1 and all that stuff. Okay, 15, please. Y equals natural log of secant of x as x goes from 0 to pi over 4. Believe it or not, this actually comes out nice, although it doesn't look like it. Okay, I checked this as problem 15 in our book. It was 13 in the previous edition, but whatever. All right, so first take the derivative. So dy dx. How do you differentiate ln something? You go 1 over that, and then times the derivative of the inside. So 1 over secant x times the derivative of secant x, which is secant x tangent x. Secant x cancels out, so I have tangent x. All right, I'm supposed to go 1 plus derivative squared. 1 plus dy dx squared is 1 plus tangent squared x. Very conveniently, that's secant squared x. So secant squared x is this, 1 plus dy dx squared. So underneath the square root is secant squared, which means I'm integrating secant. And we've seen that already. You can put it on your cheat sheet for the test on Thursday if you wish. ln absolute secant x plus tangent x from 0 to pi over 4. Okay, plug in pi over 4 here, 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 and here. Believe it or not, this all comes out to be 0. Let's see. Secant of 0. Secant is the reciprocal of the cosine. What's the cosine of 0? 1. The tangent of 0 is 0. 1 plus 0 is 1. So I'm taking the natural log of absolute value of 1. Absolute value of 1 is 1. And ln of 1 is 0. So forget about that. Secant pi over 4. It's the reciprocal of the cosine of pi over 4, which is radical 2 over 2. The reciprocal of radical 2 over 2 turns out to be radical 2. Okay, if you want, I can put that over here. 1 over radical 2 over 2. Well, when you divide by a fraction, you multiply by the reciprocal. 2 over radical 2. And if you rationalize the denominator, you just get radical 2. Because these cancel out. That's a 2 there, sorry. Okay, so again, cosine pi over 4, radical 2 over 2. Secant is its reciprocal. So take the reciprocal. The reciprocal of radical 2 over 2 is 2 over radical 2. If I rationalize the denominator, I get radical 2. Radical 2 times radical 2 is 2, so I cancel with that. Radical 2. Tangent of pi over 4, tangent of 45 degrees is 1. It's the ratio of the sine to the cosine at pi over 4. They're both radical 2 over 2. So radical 2 over 2 divided by itself is 1. So final answer is ln parentheses radical 2 plus 1. You should drop the absolute value because absolute value of radical 2 plus 1 is radical 2 plus 1, so it's just regular parentheses at that stage of the game. Okay. All right, and let me see, what else did I want to do there? That might almost be it, except for maybe, yeah, I'll set you up with 19, but I won't do very much of it. Yeah, 19, but it's going to be an etc. Also. ln 1 minus x squared between 0 and a half. All right, so what goes on here? So dy dx, 1 over 1 minus x squared, times the derivative of 1 minus x squared, negative 2x. Negative 2x over 1 minus x squared. Take the derivative, dy dx squared, okay. Well, the negative is going to go away, right, when you square it, so forget about the negative. The top is 4x squared. The bottom is 1 minus x squared squared. Now I'm supposed to add 1. So it's 1 plus dy dx squared. Okay, so here's dy dx squared, 4x squared over 1 minus x squared squared. I'm supposed to add 1. Okay, so here's 1. Do you agree? 1 minus x squared squared over 1 minus x squared squared, because I need a common denominator. All right, so take a look at what happens. The bottom is 1 minus x squared squared. Okay, distribute out the numerator. So 1 minus 2x squared plus x to the 4th. Okay, so this stuff right here is this. And then plus 4x squared. And take a look at what happens. If I add the 4x squared, instead of minus 2x squared, I'll have a plus 2x squared. So it's like this, which very conveniently factors back into 1 plus x squared squared, right? So one more time, this factors into 1 plus x squared squared. So I have 1 plus x squared squared over 1 minus x squared squared. All of that goes underneath the square root right here. So it's going to come out nice. So arc length is the integral from 0 to half of square root of 1 plus x squared squared over 1 minus x squared squared. That's a lot of squares, I'm saying. But all that happens, you know, is take off the square root and that 2 there and that 2 there. So again, I'm just going to say et cetera after this. But I have integral from 0 to half of 1 plus x squared over 1 minus x squared dx. I'll just say et cetera, because the rest of that is just going to be partial fractions. All right? So it looks like you might do the long division, and that's going to factor into 1 plus x, 1 minus x, and stuff like that. Right? So do the polynomial long division, and then after that, you'll do partial fractions. But now that's something you know how to do already. Okay, so that's as much as I was going to do. I didn't quite finish it, but that's okay. I can do more next time, introduce a little later, or maybe even I can do a little bit after the break, but we'll see. Okay, so get ready for most of the rest of today for questions and answers in preparation for the test. Okay, so I'll let you ask that. I know a lot of you had stuff on the chat, so let me stop the share and we'll break shortly, but there's a whole bunch of stuff in the chat. Let me see what I can do and what I can't do. Okay, anybody that missed a roll call, send me an email. Again, once I put it away, I don't want to pick it up. Okay, so just email me later if you're here. Can we start the test after reviewing the quiz? I'm not sure what you mean by that. The test will start after the break on Thursday, and I'll let you ask questions, so maybe that's about that. Okay. Yeah, I haven't graded all the quizzes yet. So if you didn't get that, don't worry. That's fine. Yeah, it looks like there's some confusion about the test. The test is Thursday, not today. And let's see. Yeah, Justin, I'm not reading your comment for obvious reasons. Sorry. Okay, skip 39 for 7.4. Okay, let me look at that. Yeah, 7.4, skip the last three, 39, 41, and 43. You're not responsible for 39, 41, or 43. Let's see, 70% of the homework, 70% of the total. It should be of every section. Officially, it's 70% of the total. But what I don't want you to do is do 70% and then stop and you never do anything else. That's not good for you anyway, because that means you haven't seen any of the others. So that's that. Can we have 15 minutes to send the exam? I'm not sure. Okay, try to get it within 5. Okay. Put it that way, or try to finish the test earlier. Okay, I'll probably let you have a little bit more than 5, but yeah, I know what it means that you try to click, and then it takes a while to do this and do that. Yeah, I get it. Okay. Okay, does the camera have to include our monitors? No, it doesn't. It's just like you're doing now. Okay, you just show me like most of you are right now. I have to see your actual screen and your actual background. Okay, so there's that. Okay, hour and 15 for the test. That's really up to you guys. Okay, I only promised you 50 minutes, but if you want more time, then we stop the first half on Thursday earlier. Okay, and let's see. We're on 7.8, number 19. Okay, we'll do some of that stuff after the break, I suppose, is the way I should say it right now. Okay, so it's not even 8 o'clock yet, so that's fine. So let's do this. So I will break. I might lecture a little bit more on 8.1, but then I won't go that long, and then I'll let you ask a whole bunch of questions the rest of the time. Okay? All right, so we'll break. Let's see, it's a little bit before 8, so how about 8:10? Okay, so 8:10, I'll lecture a little bit more on section 1, and then the rest of the time, you can ask me stuff in preparation for the test on Thursday. Okay, so we'll take a break, and I will run away and hide also. All right, folks, we'll start up again. It's about 10 after. Okay, I was going to show you one more problem, I think from 8.1, and then questions and answers. You can send it to the chat, or you can unmute yourselves as necessary. 7.7, the midpoint rule, trapezoid rule, and Simpson's rule. Yes, I'm probably only going to ask you one of those. I won't tell you which one ahead of time, of course. If I ask you something about all three, it's very unlikely to be, do the whole thing, or I might just say, set it up. So show me the, the 1, 2, 2, 2, 2, 2, 1, or 1, 4, 2, 4, 2, 4, 1 business, right? And then stop, something like that. I'm not promising that's what it's going to be, but that's something that might happen. Okay, I do see some questions in the chat about more time in the test. Again, that's up to you guys. So Thursday, I'll lecture not that long, questions and answers, break, and then test. So that can be as late as, I'll finish as late as 8:20, but if we finish as early as 7:30, 7:45 or whatever, that just gives you more time to do the test. Okay. And yes, I get it. If you can't, send everything within 5 minutes, I understand. So, 10 maybe, we'll see. So much material for 15 minutes. You're right. I keep that in mind when I do the test. And by the way, I'm not totally against the idea of curving the test, although that's usually not what I do. But if I find out later, say, oh yeah, okay, everybody there wasn't enough time, most people only got to question 7 or whatever, then I might decide to curve it. Now, I don't want all of you, conspiring together and say, hey, let's all only stop at problem 6 or something like that. I don't want you to do that, of course. I doubt you would be able to get that anyway. But yeah, okay. And other comments? I think I've got everything I need from the chat. Okay, so let me go back and do problem 2. And that was it. Then I'll stop. So you can have the rest of the time for questions and answers. And the more questions you get done today, that's less that you have to do next time, hopefully, right? So that goes along with the idea that maybe we can start the test earlier on Thursday. Is that right? Okay, so here we go. Get back to sharing the screen. Okay, way back to question 2, the only even one. Okay, so question number 2. Use the arc length formula to find the length of the curve y equals the square root of 2 minus x squared, x between 0 and 1. Check your answer by noting that the curve is a part of a circle. Okay, so what do they mean by that? Okay, and so let me mark this off. And then, yeah, I'd be pretty much done with 8.1, and that's the only even one. All right, so let me show you what we have. Y equals the square root of 2 minus x squared, x between 0 and 1. Okay, so first I want you to notice this. So what they're saying is show that it's part of a circle. If you square both sides, looks like this, move the x squared over, x squared plus y squared equals 2. That's the equation of a circle with a center at the origin, center 0, 0, radius is the square root of 2. So it looks something like this. But let's look at what we got. We're only going from 0 to 1. What do you get when you plug in 0? Square root of 2. What do you get when you plug in 1? 2 minus 1 is 1. Square root of 1 is 1. So you have the point 1, 1. So we're only going from here to here. If this is the point 1, 1, this would be a 45-degree angle. So what fraction of the whole circle do I have? I have 1/8, right? 1, 2, 3, 4, 5, 6, 7, 8. Or you can say this is 45 degrees. 45 degrees out of 360 is 1/8. So I have 1/8 of an entire circle. So I could take the entire circumference. The circumference of a circle is 2 pi r. And I take 1/8 of that. So the arc length is 1/8 of 2 pi r. The radius is radical 2. So 1/8 of 2 pi r, cancel right here. pi radical 2 over 4. So I'm expecting the answer to be pi radical 2 over 4, which you can see over here in the final analysis. That's what I have. Okay. Incidentally, you could use the same scheme to show that the circumference of a circle is 2 pi r. If you take any circle and do this arc length business, okay, you'll see that the formula is 2 pi r. So there's another formula that you have maybe from 6th grade or 7th grade that you can verify, you can check by the techniques of calculus, right? We have what? We have the formula for the volume of a cone. We did the volume of a sphere, okay? You could use this as the formula for figuring out the circumference of a circle. It'd be 2 pi r. This is a variation of that thought. But anyway, here we go. All right, so y is equal to 2 minus x squared to the 1/2. Y prime, 1/2, 2 minus x squared to the negative 1/2 times the derivative of the inside, which is negative 2x. Very conveniently, that 2 cancels that 2. So I have negative x on top. This is a square root on the bottom. The 1/2 means square root. The negative means it's on the bottom. So negative x over radical 2 minus x squared. All right, I'm supposed to square it. So y prime squared, or dy dx squared. The negative goes away when you square it, right? Negative times negative is positive. When you square that, you have x squared. When you square that, you just have 2 minus x squared. All right, now I'm supposed to add 1, right, to dy dx squared. So here's the derivative squared. So behind my pen is 1. 1 plus x squared over 2 minus x squared. Okay, so here's 1. 2 minus x squared over 2 minus x squared. 1 plus dy dx squared. That's in order for me to get a common denominator. So I'll just add the top. Well, if I add the top, x squared cancels. So I have 2 over 2 minus x squared. So the arc length is the integral from 0 to 1 of the square root of that mess. Okay, ignore the red for the time being. 2 over 2 minus x squared dx. Okay. We actually have one of the fundamental integrals from Calc 1. It was 1 over radical 1 minus x squared. That was your inverse sine or arc sine. Okay. So I have to force this to look like 1 minus something squared. The trick is to divide top and bottom by 2. See, I don't want this to be 2. I want this to be a 1. This might get a little bit messy, but that's okay. I can do is use substitution. Okay, so divide top and bottom by 2. That's going to become a 1. And by the way, the square root of 1 is 1. So the 1 is completely out of the radical. And divide this by 2. 2 divided by 2 is 1. And then I have x squared over 2. So it now looks like this. Integral from 0 to 1 of 1 over radical 1 minus x squared over 2. Okay, so the game I'm going to play is I need to write this as something squared. Blah, blah, blah squared. What do I square to get this? Well, I want x squared. What do you square to get 2? Radical 2. So I write it as 1 minus parentheses x over radical 2 squared. So I claim this is the same as this. If you square this, right, x squared over radical 2 squared is 2. All right, so I want this to be 1 minus u squared, so I can substitute with my arc sine. So let u be that. So u substitution, u equals x over radical 2, which you should think of as a coefficient of 1 over radical 2. 1 over radical 2x. du is 1 over radical 2 dx. The derivative of this is 1 over radical 2 dx. So before I substitute, I need a 1 over radical 2 inside, which means radical 2 outside. These two combine to be 1. Radical 2 times 1 over radical 2 is 1. Multiplied by 1. That's called the identity property of multiplication, right? You're not changing the value of the expression. All right, so there's going to be a radical 2 in front. And these limits are for x. I have to change over to u. So since I have u equals x over radical 2, I plug in 0. If x is 0, u is 0 over radical 2. That's still 0. And if I plug in x equals 1, u will become 1 over radical 2, which is commonly thought of as radical 2 over 2. Okay, 1 over radical 2 is the same as radical 2 over 2. If you rationalize the denominator, you know how to do that, right? Multiply top and bottom by radical 2, you get radical 2 over 2. So my new integral is going to go from 0 to radical 2 over 2. There's a square root of 2 outside. So my I is radical 2, integral from 0 to radical 2 over 2 now of du over radical 1 minus u squared. Okay, this is my arc sine or inverse sine. Okay, the derivative of inverse sine of u was 1 over radical 1 minus u squared. Therefore, the integral of 1 over radical 1 minus u squared is arc sine of u. I still got the radical 2 in front. So arc sine or inverse sine, they mean the same thing. Arc sine, inverse sine. Okay, from 0 to radical 2 over 2, leave the radical 2 in front. Okay, plug in radical 2 over 2. You have inverse sine of radical 2 over 2. You're really saying what nice angle is there so that the sine of the angle is radical 2 over 2. That's pi over 4. Minus inverse sine of 0 is 0 because the sine of 0 is 0. Okay, so that gives me the final answer of pi radical 2 over 4, which is what I had over here also, pi radical 2 over 4. Okay, so that's all there is about problem number 1. Problem number 2. Let you try problem number 1 on your own for that. Okay. All right, so I am done with all I was going to do for 8.1. I've done a lot of the problems anyway. So next time when we start class, I'll lecture a little bit on 8.2 and then let you ask questions. We break up until the latest is 8:20, but if we stop earlier, that's fine. You just get more time for the test. All right. Okay, so I'll switch over to question and answer mode. Okay, and I know on the chat, some of you already gave some questions. Okay, so let me tackle those. 7.8, number 19 was asked for. 7.8. And if the questions stop early today, we'll end early today also. So in other words, I got nothing else today. We have a whole hour to review for the test. I mean, I hope your attitude isn't just, oh, you know, I want to get out here early. I mean, getting out early should be a very small consideration when it comes to learning the material and doing well in the test, right? Okay, 7.8, number 19. Okay, z e to the 2z dz. So that looks like we're going to have to do integration by parts. Right? Okay, so let me write that problem down. 7.8, whoops, didn't want to use red. 7.8, number 19. And go from negative infinity to 0 of z e to the 2z dz. Okay. All right, so I think I can do two things at once. I'll change this to a b, take the limit as b approaches infinity, negative infinity. Okay, so polynomial exponential, so let u be the z. dv is e to the 2z dz. du equals dz. v equals, okay, if I integrate, I would multiply by half, since if I differentiate, I multiply by 2. So 1/2 e to the 2z. Double check, what's the derivative of this? The derivative of this would be the same thing, and then times 2. 2 cancels out, so you have that. Okay. So I equals limit b approaches negative infinity. All right, so uv. So uv is 1/2 z e to the 2z. And since that's outside of the integral, I go ahead and put the b to 0 minus limit b approaches negative infinity, integral from b to 0 of the integral of v du. So the 1/2, I can factor it out. 1/2 e to the 2z dz. Well, we just integrated that. That's going to be another half. So 1/2 times 1/2 is 1/4, right? Okay, so I can now put it all together in 1. Limit b approaches negative infinity. Yeah, you can keep putting stuff in the chat if you want me to do more problems. Go ahead and put it in the chat. I'll get to it eventually. All right, so now I have what? 1/2 z e to the 2z minus 1/4 e to the 2z from b to 0 equals limit b approaches negative infinity. Paren minus paren. Okay, plug in 0. Okay, that's 0, right? Put a 0 here, I get negative 1/4. I guess I don't need that big of parentheses after all. Okay, 0, that's gone. 0, that's e to the 1, so negative 1/4. Minus, okay, plug in b, 1/2 b e to the 2b minus 1/4 e to the 2b. Okay. Equals. So let's see, what do I get? So b is a big negative. E to a big negative, that's nothing. Okay, how about here? E to a big negative. Okay, that's big, but this is even bigger. So that's also going to be nothing. So this approaches 0 in the limit. Right? So it looks like the answer is just going to be negative 1/4. And just checking that is correct, because if z is negative, this is positive, that's negative. So it will be below the x-axis. So negative 1/4 does seem like a reasonable answer in this particular case. Okay, 7.131. 7.131. M over e to the m dm, integral from 1 to 5. M is not one of our favorite letters, but other one thing you could do is say, I don't like m, I'll change it to x. You're allowed to do that. Put an x here, x here, and x here, and then later on change it to m. The m's going to basically disappear, and so will the x. But let's leave it as m, since that's what they gave it to us. So the key for this is to bring this up as m e to the negative m dm. Bring it upstairs like that. E to the m on the bottom means e to the negative m on top. Okay, so again, polynomial exponential. So u equals m, dv equals e to the negative m dm. du equals dm. The integral of e to the negative m is negative e to the negative m. Okay, I guess you could say if you differentiate, you would multiply by negative 1. Therefore, if you integrate, you divide by negative 1. But dividing by negative 1 is the same as multiplying by negative 1. So it's the same thing. So I is equal to uv, so negative m e to the negative m. And since this is outside the integral, I'm supposed to put the 1 and the 5. Even though, yes, in the next step, I'll just put it back together again. Minus the integral of v du. There's another negative, so I'll put a negative 1 e to the negative m dm. That looks like a double negative, so I'll make them positive. Okay, I reached the bottom of my paper. I got to go back up. But what's the integral of e to the negative m? Negative e to the negative m. Okay, so I'll copy that, but put negative e to the negative m, and then I'm going from 1 to 5. Okay, so try to get all that here. Whoops, my paper flew away. Okay. So negative m e to the negative m minus e to the negative m from 1 to 5. Okay, negative m e to the negative m, and the integral of e to the negative m is negative e to the negative m. Okay, there are so many negatives here. I don't like this. I'm going to do a trick. I'll multiply by -1 and change the limits. I think it's easier that way. Okay, so make it positive m e to the negative m plus e to the negative m. Now be careful, if I multiply by -1, I only affect this and this, but not these two guys here. So now the 5 goes here and the 1 goes here. Okay, so again, if I take the opposite of this, I can switch the limits. Okay, plug in 1. I have 1 e to the negative 1 plus e to the negative 1. And then plug in 5. 5 e to the negative 5 plus e to the negative 5. So that's going to be 2 e to the negative 1 minus 6 e to the negative 5. And you can stop, you can leave it like that. And yeah, an exception to the rule of leaving your answer with a negative exponent is if you have an e as the base, you're allowed to leave it as a negative exponent. So this is an acceptable answer. You don't have to go 2 over e, 6 over e to the 5th. This is okay. Okay, then 7.3, 15, and 21 was asked for. Let's see, 7.3, 15. Okay, integral from 0 to a of x squared radical a squared minus x squared dx. Okay, so a squared minus x squared, that's the top one. So that x equal a sine theta. Okay. Remember, you can have a cheat sheet on the test, front and back, both sides. Okay. But after that, no other books or notes or people or computers or whatnot. All right, so x equals a sine theta, dx equals a cosine theta d theta. Okay, x equals 0, x equals a. Okay, if x is 0, then sine of theta is 0. Theta is 0. The sine of 0 is 0. If x equals a equals a sine theta, well, that means sine of theta is 1. The sine of what angle is 1? Pi over 2. All right, so I is the integral from 0 to pi over 2 of x squared. That is a squared sine squared theta, right? Radical a squared minus x squared, a squared sine squared theta, times dx. Dx is a cosine theta d theta. All right, as usual, this comes out nice. Factor out an a squared, 1 minus sine squared theta. And what is 1 minus sine squared theta? Cosine squared theta, right? So integral from 0 to pi over 2, a squared sine squared theta, square root of a squared cosine squared theta times a cosine theta d theta. And now that's going to become a cosine theta, right? Tell you what, I'll save a little bit of time. I'll put A cosine theta here. So now what do we have? A squared, another A squared, so A to the fourth, looks like. Is that okay? A squared times A to the fourth. I can bring that out. Sine squared, cosine, cosine. So sine squared, cosine squared. You've played that game before. So this falls in the category of two even exponents, the so-called hard case scenario. So you have to use that identity. So sine squared is 1 minus cosine 2 theta over 2. This is 1 plus cosine of 2 theta over 2 d theta. Take the 4 out. A to the fourth over 4. That's going to be difference of squares. 1 minus cosine squared of 2 theta. 0 to pi over 4. 1 minus cosine squared of 2 theta. That's going to be sine squared. A to the fourth over 4. Sine squared of 2 theta. D theta. Ran out of paper, so I got to switch to the other paper, but that's going to be 1 minus cosine 4 theta over 2. Let's see if I can remember all that stuff. So A to the fourth over 4. One minus cosine 4 theta over 2. D theta from 0 to pi over 4. All right, take the 2 with the 4, so that's going to be A to the fourth over 8 outside. Okay, integral of 1 is theta. Integral of negative cosine 4 theta is negative sine 4 theta times 1/4. Again, chain rule in reverse. 0 to pi over 4. You plug in 0, that's 0, sine of 0 is 0, so 0 minus 0. Plug in pi over 4. If I plug in pi over 4 here, 4 times pi over 4 is pi, sine of pi is 0. So these are all gone. So it looks like I have pi a to the fourth over 8 times 4 is 32. Pi a to the fourth over 32. Okay, so that's that one. And 7.321. Okay. Integral from 0, 0.6 x squared (9 minus 25x squared) dx. Now you will notice in this chart, it only gives me x squared everywhere. I don't have a 25. So what do? I got to get rid of the 25. Okay, so that means you can go something like this. Make this a little bit bigger. 25 like that, and a 5 like that. Okay, so I claim these are the same. Okay. A 25 under the radical means 5 outside the radical. So what did I insert? In fact, I should have put that in red. Make that in red. usually what I do. Okay, the red stuff equals 1. That's what I'm trying to say. 5 here and a 25 under the radical, I've multiplied by 1. Okay. The reason why I want to do that is so now this would just be x squared, not a 25x squared. Okay. And I can take that 5 outside as 1/5. So 1/5 integral from 0 to 0.6 x squared over. Okay, now it's what I want. So that 5 comes outside. 9 over 25 minus x squared dx. So this does fit the pattern of a squared minus x squared. Okay? So if this is a squared, it looks like a is 3/5. So a squared minus x squared, again, it's the top one. So x is a sine theta. So x is a 3/5 sine theta. By the way, which helps a lot, 0.6 is the same as 3/5, is it not? 3/5 is 0.6. So we use that. dx is 3/5 cosine theta d theta. X equals 0, theta equals blank, x equals 0.6, theta equals blank. Okay, if I put a 0 here, that means sine of theta is 0. Sine of what angle is 0? 0. If I put 0.6, 0.6 is the same as 3/5. So I have 3/5 equals 3/5 sine of theta. Well, that means sine of theta is 1. Sine of what nice angle is 1? Pi over 2. So I'm integrating from 0 to pi over 2. So I becomes 1/5 integral from 0 to pi over 2. Okay, x squared. Gets kind of clumsy now. 9 over 25 sine squared of theta. dx is this stuff. 3/5 cosine theta d theta. Square root of 9 over 25 minus x squared. So I square this, 9 over 25 sine squared theta. And this I can treat as 9 over 25, 1 minus sine squared theta. Right? So 1/5 integral from 0 to pi over 2, 9 over 25 sine squared theta times 3/5 cosine theta d theta over radical 9 over 25, 1 minus sine squared is cosine squared theta. Okay, I'm going to see if you can agree with me on this. Three-fifths cosine theta, 3/5 cosine theta. So that's gone. Okay, so let's see, 9 over 25, make it join this. So that's going to be what? 9 over 125 sine squared theta. Okay. Whoops. Okay, so what do I have? 9 over 125 sine squared. 9 over 125. Some pretty weird numbers here. All right, there's our old friend sine squared again. One minus cosine 2 theta over 2 d theta. Bring the 2 with the 125, that'll be 250. It's getting weirder and weirder. Integrate. Integral of 1 theta. Integral of negative cosine 2 theta is negative sine 2 theta times a half, chain rule. 0 to pi over 2. 9 over 250. Whoops, I should go like this. Okay, plug in 0, you get 0. 0 minus sine of 0 is 0. Plug in pi over 2. Okay, this theme happens a lot. If I plug in pi over 2, I'm taking the sine of pi. That's 0. Yeah. A lot of times when you do the integral of sine squared of theta for this kind of thing, a lot of times, I'm not going to say all the time, but a lot of times that's 0, and that's also 0. This is the only thing that's non-zero. Pi over 2. So it looks like 9 pi over 500 is my final answer there. Okay. All right, so I've caught up with the chat that round, but in order for me to see the chat, I have to stop sharing and then go back again. So let me stop sharing, double check the chat. Okay, so let's see. 7.325. Okay, 7.325. 7.329. 7.823. Yes, the more questions we have today, the less we have next time, which means we can start the test earlier next time. And let me see. 7.1, 9, and 13. Okay, so what I see right now is 7.325 and 29, 7.823, and 7.1, 9, and 13. And I think I'm caught up there. Yeah, hey, it's for everyone's benefit anyway. By the way, in case you're playing the strategy, you know, hey, we're getting him to do all the rest of the problems. I know, I get it, that's fine, I don't mind. I mean, it's easy to get credit on the homework. The whole idea is you have it in here so you can do the stuff on the test, right? I mean, your object is not just to, you know, I you know, snuck in all the homework. Well, what good is that if you don't know how to do it, right? Okay, so I think that's it. So I can't see the chat anymore as I go back to share the screen. Go ahead and put stuff in the chat, but I won't be able to see it until I finish these problems. Okay, let's see. 7.325 was asked for. So let me see. X squared (3 plus 2x minus x squared dx). Okay, oh, I can actually see the chat now. That's interesting. Okay. All right, the key to this one is to write this as a perfect square. Okay, so let me show you how to do that. I'm going to put negative parentheses x squared minus 2x plus 3. We had a completing the square also for problem 27, I think it was. All right, so this is still the same thing, right? Negative x squared plus 2x. Okay, so complete the square, do the half and square business. So half of negative 2, negative 1, square it, 1. This is a perfect square. But because there's a negative there, I'm really subtracting 1. So to balance it, I'm going to add 1. Okay? So these two combine to be 0. Okay? If I add 0, I don't change the value of the expression. okay, because that's really -1 and +1. Okay. So now I can write it as x squared radical negative x minus 1 squared plus 4 dx. Turn that around. 4 minus x minus 1 squared dx. All right, and I'm going to switch over to call it, let's say, t. Okay, so let t equal x minus 1, dt equals dx, and that means x is equal to t plus 1. Okay. See, I want this to be 4 minus t squared. So t equals x minus 1. If I add 1 to both sides, I have x equals t plus 1, because I need to change this over also. So I is the integral of x squared, t plus 1 squared, radical 4 minus x minus 1 is t squared dt. Okay, so now that looks like something I can do. So t equals 2 sine theta, dt equals 2 cosine theta d theta. So I now have t, which is 2 sine theta plus 1 squared, radical 4 minus t squared, 4 sine squared theta. dt is all this stuff, 2 cosine theta d theta. And I reached the bottom of my paper. But this is 4 parentheses 1 minus sine squared theta. So we know that's going to be 4 cosine squared theta, right? Okay, so I've got to use another sheet of paper. Sorry. But I'm going to square that as what? 4 sine squared theta plus 4 sine theta plus 1 times this stuff times 2 cosine theta d theta. Okay, so four sine squared theta plus 4 sine theta plus 1 radical. Oh, I know what I can do. I need to shorten this. Don't have enough hands to do everything, but yeah, better than nothing, I guess. Okay, so that's that. Radical 4 times cosine squared, right? So 4 cosine squared theta times 2 cosine theta d theta. This here is 2 cosine theta, right? 2 cosine theta. So 4 sine squared theta plus 4 sine theta plus 1. 2 cosine theta times another 2 cosine theta. So 4 cosine squared theta d theta. Yeah. Okay. I'll use this. And now I distribute. So 4 sine squared cosine squared. 4 sine squared theta cosine squared theta. Plus 4 times 4, 16 sine theta cosine squared theta. Plus 4 cosine squared theta d theta. Paren, paren. Okay, so it looks like I've got I1, I2, and I3. Whoops, this one should be a 16, right? Sorry about that. 16. So I is I1 plus I2 plus I3. And let's see, looking at the way time is going and the questions, I'm probably gonna have to just say etc. after a certain point for this one. So I1 is 16 sine squared cosine squared We've already done this a couple times today, right? So you know what to do for that. Okay. I3 is just integral of cosine squared. So make that change. 1 plus cosine 2 theta over 2. I'll do I2 in its entirety. I'll take out the 16. Okay, this fits the category of an odd exponent. Okay, so let u be cosine theta. Du is negative sine theta d theta. Negative 1, negative. So I2 is negative 16. Integral of u squared. Negative 1 sine theta d theta is du. That's negative 16 u cubed over 3 plus, well, I'm going to call it C2 because I was doing I2. There's going to be a C1 for I1 and a C3 for I3. Okay, but plug stuff back in. What was the u? U was cosine theta, so negative 16 over 3 cosine cubed theta plus C2. And I'll just say et cetera from there. Okay, because of time, I won't go on with that. But you have to do a triangle and keep going from there. Okay, but seeing that we have more questions and seeing we may not finish early after all, I want to be able to do more problems. Okay, so sorry I have to bend in that one. 29. Yeah. X radical 1 minus x to the fourth. Okay, the key for, this is still section 7.3. The key for this one is, since this is only an x, I want to write this as an x squared squared. Okay, in other words, like that. Okay, so no, I want to save u for later. How about I call it t? T equals x squared. dt is 2x dx. So multiply by 2 here, 1/2 here. So I is 1/2. So 2x dx is now dt, radical 1 minus t squared. All right, so t equals sine theta, dt equals cosine theta d theta. So I is 1/2 integral of radical 1 minus sine squared theta times dt cosine theta d theta. And this becomes cosine squared. So the square root of cosine squared is cosine. So I have 1/2 integral of cosine times another cosine. So cosine squared. Okay, so 1/2 integral of 1 plus cosine 2 theta over 2 d theta, which is 1/4. So 2 comes out. Integral of 1 is theta. Integral of cosine 2 theta is sine 2 theta by the chain root times 1/2 plus c. And to finish it, it's actually better to use an identity. We have an identity for sine of 2 theta. It's 2 sine theta cosine theta. Sine 2 theta is 2 sine theta cosine theta. The 1/2 will cancel the 2. So I have 1/4 theta plus 1/2 times 2 sine theta cosine theta plus c. Okay, triangulate. I have t equals sine theta. That's t over 1. Theta, opposite, over hypotenuse, peak elsewhere in the problem, radical 1 minus t squared. I'll let you check it. It does fit the Pythagorean theorem. Okay, so that means theta is inverse sine of t, right? Take inverse sine of both sides, so to speak, get that. Okay, so inverse sine t plus sine of theta, t, cosine of theta, adjacent over hypotenuse, radical 1 minus t squared, plus c, and then change t back even. T was x squared. So put x squared here, here, and here, and we finally have it. So 1/4 inverse sine of x squared plus x squared radical 1 minus x squared squared, x to the 4th, plus c. Okay. So that's that. 7.823. Okay, what time is it? 9:05. We may not end early today, but that's okay. At least you're getting more now, and you're asking more questions that we don't have to ask next time. 7.823. Infinity is 0. Z to the 4th plus 4. dz. Okay, I think we're going to play the same game of making this z squared squared. Like that. All right, and yeah, I should have put limit b approaches negative infinity, integral from 0, b to 0, z dz over z squared squared plus 4. Okay, so u equals z squared, du equals 2z dz. Means I need a 2 here and a 1/2 here. When z is b, u is b squared. When z is 0, u equals 0. So my integral has a 1/2 out in front. Limit b approaches negative infinity. Okay, we're now going from b squared to 0 of 2z dz, that's my du, over u squared plus 4. Oops, squared plus 4. All right, I need this to be a 1 so I can use inverse tangent. So we do the same trick. Go like that. One-half limit b approaches negative infinity. B squared to 0. Okay, this 4, I'll bring it outside as a 1/4. This is now 1, 4 over 4 is 1, plus u squared over 4, I can think of it as u over 2 squared, like so. Which means I substitute again. I already used up u, so how about I call it t? T equals u over 2. That's u over 2, half of u. dt equals 1/2 du. Change the limits again. U equals b squared. T is 1/2 b squared. U equals 0. T equals 0. Okay, so I need a half, which means multiply this by 2. Looks like these guys cancel out. So 1/4 limit b approaches negative infinity. Integral from 1/2 b squared to 0 of 1/2 du, that's my dt, over 1 plus t squared. Okay, that's my inverse tangent. So 1/4 limit b approaches negative infinity. Inverse tangent of t, 1/2 b squared to 0. Okay, inverse tangent of 0 is 0. Now, when b becomes a big negative, this becomes a big positive. Okay. Inverse tangent of a super big positive turns out to be pi over 2. So I have negative pi over 8 as my answer. Okay, if you think back to the graph of inverse tangent looks something like this. Inverse tangent. So when x gets super big, y approaches pi over 2. So it looks like I have this. And double check, yes, the quantity should be a negative. So it looks like we have that. Okay, and let's see. 7.1, number 9 and 13. Number 9. Okay. Inverse cosine. Okay, you don't really have any choice here, so that's going to be my u. dv is dx. Derivative of inverse cosine is the same as the derivative of inverse sine, except there's a negative. So du is negative 1 over radical 1 minus x squared dx, and v is equal to x. So I is uv, x inverse cosine of x, minus the integral of v du. There's another negative, so I'll put a negative 1. So I have to take your time out and figure this out. So I'm going to call that I1. So I is x inverse cosine of x, double negative, so plus I1. So work on I1. Okay, the derivative of 1 minus x squared is almost that. So regular u substitution, u equals 1 minus x squared. Du is negative 2x dx. So I need a negative 2 here and a negative 1/2 here. I1 is negative 1/2 Integral of negative 2x dx is now my du over radical u, which is negative 1/2 integral of u to the negative 1/2 du. Integral of u to the negative 1/2, u to the positive 1/2, divided by 1/2 means times 2 plus c1. Cancel, cancel, which is negative radical u plus c1. And what's u? 1 minus x squared. So negative radical 1 minus x squared plus c1. Okay, so that goes in for I1 way back over here. So plug that in and we're done. So I is, just copy that, x inverse cosine of x, plus I1, so I copy this, so minus radical. And now that I just have that, say plus c. T cosine squared t dt u dv t cosecant squared dt. Okay. Du cosecant squared integral of derivative of cotangent negative cosecant squared. Okay. uv v du. There's a negative negative 1 cotangent t. Okay, we did this a while back, but you can make it cosine over sine. Okay, let's put cosine over sine. And then do a u substitution. U sine du cosine t dt. Well, I should have called that I1, sorry. So negative t cotangent t plus I1. So I1 is du over u. So ln absolute u, ln absolute sine t. Okay, so just plug that back into here. Negative t cotangent t plus like that. Okay. Let's see what else we have here. 7.2, 35, and 37. Let's take a look. Seven point two 35. 37, I'm afraid I won't have time to do that. I can just tell you how to start it. 35, pi over 6 to pi over 2. Cotangent squared. A trick for this is to make it cosecant squared minus 1. So I'm using this identity. 1 plus cotangent squared is cosecant squared. So cotangent squared is cosecant squared minus 1. All right, integral of cosecant squared, we just did that, is negative cotangent. Integral of 1 is x. Okay, I do the same trick. I don't like all these negatives, so I'm going to make it positive and switch these two around. All right, so cotangent pi over 6 plus pi over 6 minus cotangent pi over 2 plus pi over 2. Cotangent is cosine over the sine. And pi over 6 is 30 degrees. This is radical 3 over 2 comma 1/2. This is 0 comma 1. So cotangent, you can say x over y, or cosine over sine. So that divided by that is radical 3 plus pi over 6. Okay, cotangent cosine over sine, or x over y, that's 0 plus pi over 2. Okay, so common denominator, multiply that by 3, multiply that by 3. So radical 3 pi over 6 minus 3 pi over 6 is minus 2 pi over 6, or radical 3 minus pi over 3. Okay, and finally 37, I won't have time to finish it. We're almost out of time actually, but I'll just set you up for that. Thirty-seven from 7.2. Pi over 4. Pi over 2. Cotangent to the 5th phi, cosecant cubed of phi d phi. This is phi, or phi, Greek letter. I would change this to sines and cosines. So cotangent is cosine over sine. Cosecant is the reciprocal of the sine. So I've got sine to the 8th of phi, cosine to the 5th. Well, this does fit the category of an odd exponent. Okay. So I'll separate out a cosine of phi. So that means I want all of this stuff to only say sine. I've got cosine to the fourth. Right? Cosine to the fourth is cosine squared. So this is still cosine to the fifth, right? Cosine squared, that's 4, and then 5. And then I change that to 1 minus sine squared. Okay, then you just do a U substitution. U equals sine phi. Du is cosine phi d phi. Okay, and I see we're just about out of time, but I'll just have to say et cetera for that. But that's the idea of getting it to work in this situation. Okay. All right, folks, that'll do it for tonight. So next time I will start some of 8.2, not much. Let you ask questions, then we break, and then we take our tests, okay? And you turn in your homework, you must have at least 70%, and you know the ground rules. So we didn't do it last time because last time my internet wasn't working, but you'll show your camera. I need to see you, mute yourselves, and good stuff like that, okay? All right, so that'll do it, everyone. So have a good night, everybody. See you next time. Be ready for the test. Okay, bye, everyone.
Bye, Mr. Hom.
Okay, bye.
You.
Thank you.